Whenever we're talking about a company, a firm, we always want to take a minute to think about some of the fundamentals. Where did this firm come from? Who owns it and how is it managed? Now, I'm going to let you read your textbook and get most of these details there. You probably know most of the basics. But let me raise some interesting scenarios that you might not be familiar with. Now, of course, there are a lot of different ways that you can have a firm be created. Most of the time in economics, if we talk about a private firm, we mean a firm owned by individual people or groups of individual people. It might be a sole proprietorship owned by one person, or a partnership owned by 2, 3, or even 100 people. Or it could be a stock-owned company that's traded on a market. A public firm is usually when we're talking about a government-run organization. And a nonprofit firm is one that is not designed to earn a profit. But let me tell you a story about one I'm familiar with. In grad school, I met some people who worked for a nonprofit retirement community. It was hundreds of acres, huge campus, and it was one of those communities where the way it works is you buy a house and you're never going to get that money back. In exchange for buying the house, it's guaranteed that somebody is going to be there to take care of you throughout the entire rest of your life. They had libraries, a place where you could get meals, and doctor's offices. And the way it worked is you live in the house as long as you can, and then when you can't take care of yourself, they move you into more of a group retirement home or an apartment. And when you can't take care of yourself in that kind of situation, if you need more medical care, they'll move you into a nursing home. So again, you pay a large fee up front. You buy a house. You're not going to ever be able to sell the house, but you get a guarantee in exchange. I met some of the people who created this nonprofit firm, and I asked them, why did you do this? What incentive did you have to create this nonprofit organization? He said, look, there's two things going on here. First of all, even though it's nonprofit, we took a lot of risk by putting up the money to buy the land and advertise and get this whole thing started. Took a lot of work. But the first way the partners made money is that we loaned money to the nonprofit corporation at a nice high interest rate. And so we got a lot more money loaning the money to the retirement community than we could have earned in a bank. The second way these partners who got together to create the nonprofit firm made money is they were being paid to manage and getting consulting fees, and so they paid themselves salaries. So just because something's a nonprofit firm, it doesn't mean that no one is really making a return on their investment. Now, some nonprofit firms, like Blue Cross Blue Shield is another one, they're enormous multi-billion-dollar companies. And even though they're nonprofit firms, there are many people who are making a lot of money working for and managing these firms. Now, it's not always the case that a nonprofit firm is going to have a lot of people making a lot of money. My wife works for a nonprofit charity, and no one at the charity has a salary. It's all 100% volunteer. So instead of making money, we actually put money into this nonprofit. The charity she works for solicits donations for food to feed kids who normally during the school week would get free lunch and free breakfast. But over the weekend, they're kind of left out in the cold and they might not have enough food to eat. So her organization collects food, puts it in backpacks, drops them off at schools on Fridays so that these students can have something to take home to eat during the weekends. So nonprofits can run the gamut from truly volunteer charities where no one makes anything all the way up to multi-billion corporations. So when it comes to the ownership for-profit firms, there are a lot of ways that can happen. Sole proprietorship, partnership, limited partnerships, and corporations. I'm not going to go through all the details because you've probably heard this before somewhere else. If you haven't, pay attention to the textbook on this. But one thing as economists we always want to think about is the difference between what owners want and what the managers might want. Now, sometimes in a company, the owner will also be the manager, but most often this is probably not the case. So what is it that in economics we assume that the owners of companies want? Well, the goal of a firm is usually assumed to be to maximize the amount of profit that you earn. On the other hand, suppose you're the manager of a company. What might you want? Well, a lot of times what managers want isn't aligned with what owners want. From studying many different companies, quite often what we see is that managers want to make their job bigger and more important. So they want to make their budget bigger. They want to make the number of employees that they oversee bigger. That way they feel more important. They have more dominion and more control over more people. So sometimes we see managers just wanting to spend more, hire more people, and that might be at odds with what the owner's goals are. So this is a big area of study in economics. So as we've discussed a little bit before, when we're talking about long-run production functions versus short-run production functions, in the long run, what kinds of things are we planning and deciding? Now, with a long-run production function, everything is variable. It's a long enough period of time to where we can change the amount of labor, land, capital, and entrepreneurship, even a long enough time to change those things to zero. So it's got to be a long enough time to scale up our business, scale down our business, or exit this industry altogether, permanently using all of our inputs for some other purpose. So if we have a production function like this one over here, Cobb-Douglas, Q equals 10 times L to the 0.6 times K to the 0.4. Let's practice again taking a partial derivative to find the marginal product of labor function and the marginal product of capital function. Marginal product of labor is the partial derivative of output with respect to labor. So remember what we do is we hold everything constant except for the variable that we are looking about how it affects output. So we can just write down the 10, which is a constant. We're treating the K to the 0.4 as a constant, and we take the derivative of the L to the 0.6 part. So we're going to multiply by the exponent, 0.6, and then subtract 1 from that exponent. What's that exponent going to be? Negative 0.4, right. 0.6 minus 1 is negative 0.4. So then we just want to simplify this. We can group the 10 and the 0.6. 10 times 0.6 is 6, times K to the 0.4, times L to the minus 0.4. Now, let's do the same kind of thing with capital. The partial derivative of output with respect to capital. We're going to treat the 10 times L to the 0.6 as a constant and take the derivative of the K to the 0.4 part. So multiply by the exponent, 0.4 times K, and subtract 1 from the exponent, minus 0.6. And then we can just simplify that a little bit and clean it up. 4 L to the 0.6 times K to the minus 0.6. So this marginal product of capital function, if we plug in how much labor and capital we have right now, it'll tell us at what rate output would increase if we added one more machine. What about average product of labor, or output per worker? The function that we're looking at is Q over L, output per worker. Another name for average product of labor is productivity. So when we talk about the productivity of labor, this is what we'd be talking about. Now, if we use some algebra, we can take this Q function up here and then divide it by L and see what happens. So 10 L to the 0.6 times K to the 0.4, divide that by L, Simplify that, and we get a productivity function, output per worker. So we just say 10 L to the minus 0.4 times K to the 0.4. Now, notice how this function is pretty similar to, but different from, the marginal product of labor function up there. Those two are related, but they're not the same thing. So all that was assuming we were in the long run where we can change labor and capital. In the short run, we're going to assume that something's fixed. And in this case, it's going to be capital. So we're going to have a certain number of machines, and we can't change that today. Today, let's assume that the number of machines we have is fixed at 8. We can't increase the number of machines today, and we can't decrease it either. We're just stuck with 8 machines. So if we want to produce more output, we have to use more workers to do that. So today, as we increase and decrease the number of workers, that'll change our costs and change our output. So in the short run, a fixed cost would be the fixed input, the cost of the capital. The variable costs would be the cost of the labor, since that's what we're varying as we produce more today, right? So we can't change the number of machines, fixed costs. We can change the amount of labor. That's the variable costs. A variable cost is anything that we use more of and costs more as we produce more units. Now, when we're doing problems with production, total product is just another word for the amount of output, or Q. So how many units of output are we producing today? Marginal product of labor, we're talking about either a slope or a derivative. The change in output divided by the change in labor. So when we're using a table down here, it's going to be interpreted as a slope. A derivative is also a slope though, right? So if we had a function, we'd do a derivative. With a table, we calculate a slope. Average product of labor, as we talked about before, Q over L is output per worker. So this is a kind of exercise you'd normally do in an introductory micro kind of class, but I think it's really important to review. So as usual, when we're calculating marginal product, we can't do it when we're talking about 0 workers and 0 units. Average product also doesn't make sense. 0 divided by 0, we just can't calculate it, right? So since marginal product is change in quantity over change in labor, there's no change if we're just sitting there with 0 workers and 0 output, right? Average product, Q over L, 0 divided by 0. As I said, we can't do that. But here, when we hire the first worker, go from 0 to 1, and our output goes from 0 to 5 units of output, then what's the marginal product of labor going to be? It's going to be the change in output, 5, divided by the change in the number of workers, which is 1. So 5 divided by 1 is 5. And that just tells us the first worker adds 5 additional units of output. What about the productivity? Well, output per worker is 5 divided by 1 is also 5. It just says when we have 1 worker, we're getting 5 units of output per worker on average. Now, what about when we hire the second worker? Well, we get 13 more units of output, and we're hiring 1 more worker again. So the marginal product is 13 divided by 1, which is going to just be 13. So that second worker gives us 13 additional units of output. And our average product is 18 divided by 2, which is 9. 9 units of output on average per worker. So now I want you to pause the video to make sure that you understand how to do this. Fill out the rest of this table and make sure that you understand it, and I'll come back and show you my answers. Okay, so here are my results, except I decided to leave the last couple of marginal products blank here so that we can talk about them, make sure we see what's happening. So what's the marginal product of the 11th worker? 0, right? We hired an 11th person and we got no more output. What's the marginal product of the 12th worker? -2. We hired another person and we lost 2 units of output. The marginal product of the 13th worker is -4. So we see with both marginal product and average product that it starts low, reaches a maximum, and then starts decreasing again. These happen at different places and at different rates. The maximum productivity is at 5 or 6 workers. The maximum marginal product is around 4 workers. It's important that we think about the relationship between marginal product and average product, and we'll get to that in a little more detail in a minute. Marginal product. If we look at this graph on the right side here, marginal product tells us the slope of the production function. So we find that the slope is steepest at 4 workers. Now, if we connect these dots on the graph, we can see the slope between each pair of points. It's flat, then steeper, and it's steepest right here. And then it starts getting a little flatter, and then eventually it turns negative there at the very end. Now, one way to view productivity on a graph is to look at the slope of a ray from the origin to a point. So let's do that and see what that looks like. So here I have a purple ray from the origin to a point. The slope right there is the rise, which is 104. If we're going to that blue point, let me adjust this a little bit here. So the rise is 104 and the run is 13, right? So 104 divided by 13 gives us this productivity of 8. That's the slope of the ray. Now, let's look and see what happens to the slope as we move the ray to point to different points. What's happening to the slope of this purple ray? When I move it one point back, it gets steeper, right? And that tells us that the productivity is higher and higher and higher and higher. Now, at what point should it be the steepest, the highest productivity? Well, when the productivity is highest, that should be at 5 and 6 workers. We saw the slope was 15 at both those points, so the slope is the same. But as we move to more workers, it gets lower. And as we move to even fewer workers, it also gets flatter, you see? So it's not as steep as it is at 5 or 6. So this is just a very quick way to look at a production function and see what the productivity is. Now I want to show you something interesting about how you can tie what we're doing here into a little bit of econometrics. Suppose we took our data here, the amount of output and the number of workers, and we put them into an econometrics program or Excel or Stata, and we did a regression to try to estimate this function using a polynomial. Now, quite often, it's more convenient, believe it or not, to have an equation instead of dealing with a huge table like this. So let's see how well that works. Now, when we put this data into a regression function, we can get the following equation. Y equals 11.35 times x plus 0.9931x squared minus 0.0984x cubed, where x is labor. We get an r squared of 0.9866. Now, what does that mean if you've had econometrics? Well, the highest it could get is 1, and it tells us the percentage of the variation. In other words, the variation ups and downs in output. So it tells us the proportion of the variation in output that can be explained by the number of workers and the number of workers squared and cubed to help us fit a curve. Now that's pretty good. 98.66% of the variation is explained. 100% is the best we could possibly do. So as long as we think that equation is a pretty good model that helps explain output using the number of workers, then we could use that function and do some math on it. How could we come up with the marginal product of labor function using this equation? Of course, we'll take the derivative, right? The derivative of output with respect to labor, and that'll give us an equation for the marginal product. So 11.35 plus, and then multiply by the exponent, 1.986 times L, minus 0.2952 L squared, subtracting 1 from that exponent. So we see that this would be the function of a parabola, right? Because it's got the squared term. So this function of a parabola is going to look like either a U or an upside down U. In this case, it's an upside down U because it starts out low, reaches a maximum, and then starts decreasing. So we can kind of picture in our minds what that would look like, right? So we know where the maximum occurs from looking at the table. Now, what about the productivity or average product of labor function? That's just Q over L. We just take our equation and cancel one of the L's out of each term, right? So take the polynomial, divide it by L, and we're just going to get 11.35. That L cancels. And then cancel one of the second L's. So 0.9931 L to the first minus 0.0984 L squared. So again, it's going to be a parabola, but a different parabola compared to the marginal product of labor function. Those two functions are related, but they're different. So a parabola, it starts low, hits a maximum, and then decreases, but they're going to be reaching their maximums at different points, right? So let's look at the next page of the handout and think about how these two functions are related to each other. So here's our production function, and remember how we went through how the slope tells us the marginal product of labor? An array tells us the productivity, the slope of a ray to a point. The slope along tells us the marginal product of labor. So we can see how those two slopes would be related. Let's graph the two functions, marginal product of labor and average product of labor. This is a really important thing, so pay attention. A very common relationship in economics is the relationship between a marginal and an average function. Think about marginal and average as a metaphor thinking about your grades. Now you know what the average in your class is, right? Think about the marginal, the blue, as meaning the additional grades you earn in a class over time. Let's suppose at the very beginning here, you only have one grade. Then that one grade is both the marginal and it's your average, right? The marginal and the average are going to be the same number. So if we look back at our table for the first worker, that marginal and the average were both 5, right? So let's label that on our y-axis here. So the first quiz you have, you get a 5. That's your marginal and your average, the same number. Suppose on the second quiz, you get a higher than a 5. Maybe you get a 13 here, right? What's that going to do to your average if you score higher than your average? Well, when you score a marginal score higher than your average, it brings your average up. As long as your additional grades are all higher than the average, it's going to bring your average up, right? So then suppose, even though you're still scoring higher than your average, your grades start to drop off a little bit. As long as your grades are higher than your average, it's going to bring your average up. But at some point, you're going to score a score equal to your average. But if that score is the same as your average, it's not going to change your average, right? So your average is 15, you score a 15, nothing happens to your average. But then suppose your grades continue to fall. As your grades fall below your average, it's going to pull your average down, right? In brief, anytime you score higher than your average, it pulls your average up. Anytime you score below your average, it's going to bring your average back down. So we have these two parabola-like curves. It's a simple relationship, but it's incredibly important to think about and remember. We're going to see this a lot in this class. So there are two additional things I want to go through real quickly before I end this video. The first idea is the law of diminishing marginal returns. It's a short-run concept. Remember, in the short run, one thing is fixed at least, right? So the law of diminishing marginal returns says, what has to happen if I only increase the amount of one input, holding everything else constant, say labor? The law of diminishing marginal returns says, okay, look, suppose I've got a factory with 8 machines. Suppose I just keep piling on workers and workers and workers. When I add more and more workers sharing the same number of machines, more people have to share the existing equipment. The law of diminishing marginal returns says that at some point the marginal product has to start going down. What we're saying here is that total output could keep going up and up indefinitely, but it needs to start going up at a slower and slower rate. The additional output has to get lower and lower as I keep cramming more and more workers onto the same equipment. Instead of 8 machines, let's make this simpler. Suppose you have a company with 2 computers. If you hire one person, they're going to be very productive, high marginal product. Hire a second person. The second person would also probably have a high marginal product because the second person would also have their own computer. But the third person is going to have to share with someone, and the fourth, and the fifth, and the sixth. As more people have to share the same number of computers, you might be able to get more output, but each additional person is going to increase output a little less and a little less. In other words, the slope of a production function has to get a little flatter, and flatter. It levels off, approaching some sort of maximum in the limit, right? So the law of diminishing marginal returns does not say that output should go down at any point. It just says that it needs to go up at a lower rate. And it also says it can't keep going up at a higher and higher rate, that our production function can't get steeper and steeper and steeper as we hire more people and the equipment gets thinner and thinner. The same kind of idea can be used for farming or any other kind of enterprise. If you want to grow more wheat, we can add more water, right? But if we're only adding more water and we're not adding more seeds, land, labor, and more sunshine, then there's got to be some limit to how much we can grow if all we're doing is adding more and more water. We can't feed the entire world. If we just add more of one input, we need to add more of all inputs. Now, returns to scale is a long-run concept. Here we're talking about what happens to output if we scale up all of our inputs at the same time. More land, more labor, more capital, and more entrepreneurship. These are very different concepts. The names kind of sound similar because they both have the word returns in there. But when we're talking about returns to scale, the idea is we have increasing returns to scale if, suppose we multiply all our inputs by some number x, some number bigger than 1. Let's just call it 2 for simplicity, okay? So it doesn't have to be 2, but this is an easy way to think about it. We multiply all of our inputs by 2. Double the labor, double the capital, double the entrepreneurship. What happens to output when we double inputs? If we have increasing returns to scale, then our output is going to more than double. go up more than by this X factor, right? So we double our inputs and we triple our outputs. That would be increasing returns to scale. Decreasing or diminishing returns to scale would mean maybe we double our inputs, multiply them by 2, same as we talked about before, but now our output less than doubles. Maybe our output only goes up by 30%, right? It goes up to 1.3 times what it was before. That would be decreasing returns to scale. Now, why is this important? Because if we double our inputs, it doubles our costs. And if our costs double, but our output less than doubles, then our cost per unit, cost divided by quantity, has to be going up. Increasing returns to scale, if we double our costs, but our output triples, then our cost per unit has to go down because costs went up at a slower rate than output did. Constant returns to scale is the boring case where we multiply all our inputs by 2 or 3, and then our output also gets multiplied by exactly 2 or 3, the same amount. We double our costs, we double our production, our cost per unit is going to remain constant, right? We're going to look at this idea in a little more detail in a later lecture. So make sure to review these ideas. There's a lot of them, especially this idea about how a marginal and an average are related. It's one of those things where if you use that metaphor with grades, it'll be easy to remember, and it's a really critical concept to think about in many different situations. I wish you the best of luck in your studies. We'll come back next time and study this some more. Talk to you later. Bye-bye.